There's this process happening all around us, all the time, even inside our own bodies. That's kind of one of the most fundamental forces in the universe. It's called radioactive decay. And yeah, it can sound a little mysterious, maybe even intimidating, but it's actually the invisible engine that powers our planet, helps us read our own history, and has completely changed our world.
So, let's start with a bit of a riddle. What on earth is the connection between a dinosaur fossil, a nuclear power plant, and the molten core of our planet? I mean, they seem totally unrelated, right? But the answer to all three is, you guessed it, radioactive decay. And we're about to connect all those dots.
To really get this, we've got to go back in time. We're talking the late 1800s, when scientists stumbled upon this mysterious glow. It was a brand new kind of energy, and for the life of them, it couldn't figure out where it was coming from. It seemed to break all the rules.
What's just wild is how fast this whole thing unraveled. It kicks off in 1896, almost by a complete accident. Henri Becquerel notices that some uranium salts can fog up a photographic plate, even when it's wrapped up in the dark. Just 3 years later, you have Ernest Rutherford already figuring out there are different types of these rays. But it was Marie Curie who really saw the big picture. She realized this was a massive deal. It meant one of two things. Either the most fundamental law of physics, that energy can't be created or destroyed, was wrong, or atoms could actually change from one thing into another. A revolutionary idea.
And this is the guy right here, Henri Becquerel. He wasn't even looking for radioactivity. He was studying how some materials glow after you expose them to light. But his little pile of uranium salts just kept glowing, all on their own. It was a total accident that revealed a brand new property of the universe.
So, Marie Curie and her husband Pierre went on to discover new elements like radium that were way more radioactive than uranium. But they also learned pretty quickly that they were dealing with something incredibly powerful. This quote from her is, well, it's chilling. It shows that right from the beginning, they knew this amazing discovery came with some serious, unknown dangers.
Okay, so what is actually going on inside these strange atoms? Well, it all boils down to something we can all relate to, really. Just trying to find a little stability.
Here's the core idea. Some atomic nuclei are just built, they're unstable. They've got a wonky mix of protons and neutrons. To calm down and get stable, they have to throw off some energy and particles. That whole process, that's radioactive decay. And in doing it, the atom literally becomes a different element. It's modern-day alchemy, but performed by nature itself.
This is just a brilliant illustration of how they first started to figure this stuff out. They shot these mysterious rays through a magnetic field, and look what happened. The beam split in three. One part curved one way, another curved the other way, and a third just went straight on through. That told them everything. They were dealing with three different things, one with a positive charge, one with a negative charge, and one with no charge at all. And that's how we got alpha, beta, and gamma.
And those differences went way beyond just their electrical charge. This classic visual shows their other big difference, stopping power. An alpha particle is like a bowling ball, big and heavy, but you can stop it with just a piece of paper. A beta particle is more like a bullet. It'll go through the paper but get stopped by a thin sheet of aluminum. But gamma rays? They're pure energy, like an X-ray on steroids. They'll blast right through and need thick lead or concrete to stop them.
All right, so we know what radioactive decay is. The next huge question was, when does it happen? And the answer is one of the coolest paradoxes in all of physics. It gives us a way to tell time on a cosmic scale. And this is where your brain starts to melt a little bit. If I have one single unstable atom right here, there is absolutely no way, shape, or form to know when it's going to decay. Could be in the next second, could be in a billion years. At the individual level, it is completely, totally random.
But, and this is the magical part, even though one atom is random, a whole bunch of them are incredibly predictable. That's what half-life is. It's the exact amount of time it takes for half of the atoms in a sample to decay. And that time is always the same for that substance. It's a rock-solid, reliable clock.
Take carbon-14, for example. You've probably heard of carbon dating. Its half-life is about 5,700 years. So if an ancient tree had, say, a pound of carbon-14 in it when it died, after 5,700 years, exactly half a pound would be left. After another 5,700 years, a quarter pound. It's how we can date ancient bones and artifacts so precisely.
Now, check this out. Compare that to uranium-238. Its half-life is 4.5 billion years. That's about how old the Earth is. This super slow, super steady decay is how geologists can date rocks that are billions of years old. The range of these clocks, from tiny fractions of a second to the age of the universe, is just mind-blowing.
So speaking of uranium, it's the perfect way to see how this stuff works in the real world. Because it turns out that not all uranium is the same. There are different versions, or isotopes, and understanding the tiny difference between two of them is basically the key to the entire nuclear age.
Okay, this table nails it. You've got uranium-238 on one side. That's more than 99% of all the uranium in the ground. It's the common stuff. On the other side is the super rare uranium-235, less than 1%. But that tiny fraction is the one that matters. Why? Because U-235 is fissile. That's the magic word. It means you can split it with a particle and it releases a ton of energy and more particles, which can then go split other atoms. It can start a chain reaction. U-238 just can't do that.
So here's the simplest way to think about it. Fissile U-235 is like dry kindling. It's ready to burn and start a fire. U-238 is what we call fertile. It's more like a big green log. It won't start the fire, but if you put it in the fire, it can be converted into something that will burn. In this case, plutonium-239, which is also fissile. So one is ready to go, the other can be made ready.
So if you want a really easy way to remember this, just think 235 is the source of the power, whether that's for energy or for bombs. And 238 is more passive. It's the vast majority, but it doesn't do the heavy lifting on its own.
All right, let's zoom the camera all the way back out now, because this isn't just about atoms in a lab or a power plant. Radioactive decay is everywhere. It's a fundamental force that's been shaping our planet and really the whole universe since the very beginning.
I mean, think about it. The heat that keeps the inside of our planet molten and drives plate tectonics and volcanoes, a huge chunk of that comes from the slow, steady decay of elements. When a giant star explodes, the afterglow we see for months is powered by radioactive decay. We use it in medicine to track chemicals through our bodies. And of course, it's the ultimate clock, letting us read the history of our planet and the life on it.
So we end up right back where we started, but now we know the answer to the riddle. Radioactive decay is this constant, invisible engine humming away beneath almost everything. It makes you wonder, doesn't it? What other amazing, invisible processes are out there, secretly running the show, just waiting for us to notice? Thanks for tuning in.